Okay, so this is problem number 9 from your packet on 7.4 on rotational dynamics. So we will be doing a little bit of forces here, but a lot of this is kinematics. But it's just something interesting to think about because, in fact, one of you asked this question in class. How does the spinning affect our weight? And we'll kind of talk about that as we get through this. Because you're kind of, wait, if we're moving around the center of the Earth, and we're probably moving pretty fast. And if we're moving pretty fast, is that not enough to kind of maybe throw us off? Okay, so that was kind of the logic behind this one. I don't remember if I made this problem up, if I stole it from somewhere. I probably stole it. That's my way. I don't write very good questions, as you'll see with part F, which is mine. I couldn't quite figure out how to word it. Anyway, so let's begin with how fast are you moving around the center of the Earth if you're at the equator? Okay, so we're taking our reference frame to be the Earth itself, okay, and I'll draw a giant globe to represent that. And I'll draw this line to represent the equator and a dot to represent us. And we'll imagine we're standing at the equator and we're moving, around the Earth to the right. And in fact, I will note that I did just look it up because I was kind of like, which way do we go? Do we go clockwise or counterclockwise around? And it turns out that around the equator, our angular speed, if viewed looking down on the North Pole, according to the interwebs, our omega is positive, meaning we have a counterclockwise movement. Okay, so anyway, so my picture is correctish. It's obviously not perfect. All right, so how fast are you moving around the center of the Earth if you are at the equator? Okay, by the way, I'm not going to do givens and requireds here. There's just too many of those, so we're just going to kind of walk through it. All right, so if I want to know the velocity at the center of the Earth, okay, then I need to know, the equation is r times omega. Now you might say, wait, why are we going with r omega? We don't know omega, and we got r was given. I'll go ahead and convert r into, meters or something we can use with. But but why? What is omega? Okay, and this is something that surprises me many times that my students get tripped up on, is the omega of the Earth going around its own axis, which you should know that the omega is, the omega is one rotation per day, right? Okay, or one rotation every 24 hours, so we can convert that day into 24 hours. And so what I'm going to do is, this is just a conversion factor, and I'm just going to convert until I get the number of rotations radians per second, okay? And we're going to get 7.2722 times 10 to the negative fifth rad per second, right? If we combine that with my radius in meters, which is a rather large number, I did not go through the steps for that conversion. I'm assuming that you can do that. 6.37 essentially times 10 to the 6th meters. Okay, then basically I can plug into this equation, velocity equals radius times omega. Okay, and we will get a velocity at the equator of more or less 400 to 3 sig figs, which is probably too. I guess that's not too many. Yeah, we've got 3 here. 464 meters per second, which is quite fast. Okay. Now, what if you were at 30 degrees? So the B part is, what if you were at 30 degrees latitude? So this is the exact same question. However, it requires, a little bit of understanding of how how latitude works. And you guys have probably never thought about it because you usually see it on a map. But basically, what the latitude is, it's the angle between your current position. Between your current position and the equator line. So I can't really explain it. So what I'm going to do is I'm going to draw it on a picture. So imagine you're standing somewhere out here. Now, if you are at latitude 30 degrees, you are at a position up here where this is 30 degrees right here. Okay, which means that your radius, okay, is a little bit different. You're traveling on a different circle, okay? Around the center of the Earth, okay? So how would we define that distance, that new r, right? You do have a different radius. And so that, if you look at the picture and you can kind of understand it, well, that's going to be r times the cosine of 30 degrees, okay? Which means essentially that we can take the old answer and just multiply by the cosine of 30 degrees. Okay, so we can do that same equation we just did, V equals R omega. Okay, where the R in this case is that initial number, 6.37 times 10 to the 6 meters, cosine 30 degrees, times our angular velocity of 7.27 times 10 to the negative fifth radians per second. Okay, and we get at 30 degrees, we end up with 401 meters per second. Okay, so a slightly different value. And as you can imagine, and if you look at the kind of the equation that we did to solve this, you can see that if theta were 90 degrees, then you're standing on the North Pole. So cosine of 90 degrees, as you know, is 0. So your velocity would go down to 0. As you can imagine, you're standing on the North Pole. You would only be spinning. You would not have any tangential velocity. So it would go to 0. So that makes perfect sense. Okay, part C. Let's see here. How does this speed compare to the speed of sound in air? Okay, and really, when I wrote this, I kind of wanted the speed of air at the equator, but it doesn't really matter. Both of these are faster than the speed of sound in air. So I wrote 340 meters per second. I think on my initial key, I wrote 331 meters per second. The reason that there's some discrepancy on the speed of sound in air because it depends on the temperature of the air. I'm just going to use 340 for this particular problem. And so what we would do is we would say, okay, so we would basically divide these numbers by the speed of sound in air. And if we do so, then what we would get is that at the equator, my speed of movement is 1.4 times the speed of sound in air. And at 30 degrees latitude, which is more or less where we are in New Orleans, my speed of, I'm going 1.2 times the speed of sound in air. Okay, so then, like some of you who know some physics, we don't talk about sound very much in this class, but that means that right now you're moving faster than the speed of sound in air. And so you might wonder, wait, so how come there's not a sonic boom? How come there's not some other interesting things going on? And I want you to remember that the air that is, or all around us is also moving at that speed. Okay, so that is why we don't have a sonic boom, is that you need to be moving at 340 meters per second through the air. And right now we are moving, basically us and the air, all of it is moving at 30 degrees latitude at 401 meters per second. So relative to the air, like if you're sitting still and the air is not, and the wind is not blowing, you're not moving, you have, then there's not going to be a sonic boom, right? You need to move 340 meters per second through the air, okay? And so we would have to go a lot faster to make that happen. And we would have to do that independent of the Earth, right? We would somehow have to fly or something, or move through a car or whatever, so that we're not, so that we're not moving with the air. Okay. Find the centripetal acceleration needed to remain on the equator. What I mean by remain on the equator I just mean you're standing on the equator. Okay, so to get that centripetal acceleration. Okay, so to get this acceleration, the centripetal acceleration at the equator required to keep us needed to remain at the equator. And what I mean by remain at the equator is basically if this centripetal acceleration were smaller than this value, we would not be maintaining our distance from the center of the Earth. We would start to fly away. So let's go ahead and do that. So we're looking for AC, acceleration towards the center. And just to be a little bit easier here on myself, I'm going to use R omega squared. I don't think this is the way I did it on the key, but this is totally fine. So AC would be R, which we're going to use that 6.37 number times 10 to the 6th meters, 6.37. And then we will multiply that times omega squared. And the omega is 7.27 times 10 to the negative fifth rads per second. Okay, so if we multiply those numbers, we're going to have to square that, right? We'll get AC equals, looks like we're going to get 0.033704 meters per second squared, okay, which is a pretty darn small number. So let's say AC equals 0.0337 meters per second squared for our official answer. Okay, which is like really, really small, right? Okay. So part E, how does that centripetal acceleration compare to the acceleration provided by gravity? Okay, I can put G right underneath it, and you can see that, wow, it's like much, much smaller. If I wanted to do it like fractionally, I could say, okay, well, AC over G is, well, what is that? So AC over G is 0.003437 or 0.00344, or if you prefer, 0.344%, right? So it's less than 0.5%. So the acceleration due to, the centripetal acceleration required to keep us on the planet is only 0.344% of the acceleration provided by gravity, okay? Let's see. So then the part F, and this is the one that I dislike the way that I wrote it, but I kind of wanted to think about when I created this problem, is it says, so how does F equals ma compare to all this? So the point here is that you are being accelerated downwards by the force of gravity, and that is more than enough to account for, the spinning of the Earth and its desire to throw you off. And in fact, really G, if you wanted a correction factor for it, for the fact that we are moving, your correction factor would be what we just solved for, essentially. It would be 0.344% error is kind of what because when we do our calculations, we do not account for the fact that we are moving. Or at least I do not believe we do. It would be fairly easy to do Newton's law of gravitation, which I haven't taught you guys yet, and figure that out. Anyway, I'll have to ask Mr. Keene, but I don't think so. I think we would need fairly precise numbers to kind of, figure out a 0.344% error anyway. So, okay. Anyway, how long would a day take if the Earth were spinning fast enough to throw us off? Okay, so for this particular portion of the problem, we are going to be looking for the what do they call it? The omega. Anyway, so let's go ahead and figure that out. So in order to get this, I need a free body diagram, right? So what I'm going to do is I'm going to draw me standing at the equator. Okay, I guess I didn't put this in the problem, but I'm going to assume that this means at the equator. Okay, so because we could use either set of numbers. It's going to be harder to throw you off at 30 degrees latitude than it would be at the equator. All right, so anyway, so you're at the equator. You're kind of standing there. Here's you. Okay, and let's see. So the radial direction in this case is coming out of your head, right? That's the radial direction because that's away from the center of the Earth. The tangential direction is to the left or the right or whatever it might be. Okay, now what forces are on you? Well, at the moment that you're being thrown off the Earth, well, let's see. So the force of gravity, so you still have the force of gravity. That's the Earth pulling downwards on you, all right? And, normally there's a normal force that we would draw right here. However, at the moment you're being thrown off the Earth, the normal force goes away, right? So you have starting to take off because you are moving so fast in the tangential direction. So you have no normal force, which makes this problem not that terribly hard, okay? Okay, so let's see. So there's my free body diagram. So let's go ahead and do my equation. So the sum of the forces in the r direction equals ma sub r. Okay. Let's see. So in the r direction, the only force we have is the force of gravity, and it's going downwards, negative f sub g. We're going to leave that right-hand side alone, ma sub r. Okay, and we will kind of keep rolling. We will say negative mg. Okay, so that's expanding the left-hand side. And on the right-hand side, we're going to make a note that, well, obviously we have the m, but, what I'm looking for here is omega, right? Because I want to know how many rotations, maybe per hour, per minute, whatever. I don't know how fast we're going to have to go. But I'm going to use r omega squared here instead of v squared on r, because I want to remember that what I'm looking for here is omega, right? So that's kind of the key, right? So if I want omega, then I'll solve for it. I mean, I guess I could have solved for V, but then I still would have had to go the one extra step to get omega. So I'm not going to do that, okay? So we've got the physics right here, right? And what's happening here is you're moving so fast that there's no force holding you out, right? You're moving at this critical omega, which is going to, where the force of gravity is exactly strong enough to hold you at that distance, okay? So you're almost like a satellite, but you're rotating around the Earth at, a millimeter or whatever's, a nanometer above the Earth's surface or whatever, okay? So anyway, so no, that's really the physics right here is this equation. So if we solve this equation, right, so first thing I'm going to do, I'm going to get rid of those positive signs because they aggravate me. Those negative signs, turn them into positive signs. And then I'm going to get omega equals, and I love how simple this is, the square root of g over r. That's like super duper easy if we rearrange this. So let's see, let's plug in some numbers. Equals the square root of 9.81 meters per second squared, and we'll divide that by the radius of the Earth, which is 6.37 times 10 to the 6th meters, right? So note that underneath that radical, we end up with a per second squared, which means when we divide this thing out, I'm getting a per second, which means we're getting radians per second, right? So this is a very, very small number, 0.0012407 rads per second, right? And it's kind of useless to me. So because if I want to know how long a day takes, because that was we wanted omega in essentially something that tells us the time per rotation, right? So let me go ahead and convert this. I'm going to do an interesting conversion because I want time per rotation. And note, I've got some version of, well, this is rads per second, but I essentially have rotations per time here, right? Like that's not really where I am, but I can convert it to that. I want time per rotation, right? So I'm going to invert this. I'm going to do 1 second per 0.0012407 rads, right? So, and if I convert this, let's see, so we get 2 pi rads over 1 rotation. And I do 3,600 seconds in 1 hour. And that should give me the number of hours per rotation. Let's see if that's a reasonable number. And so we plug that out, I get 1.4067 hours per rotation. So basically our day is essentially 1.41 hours, like super, super fast, right? Anyway, so hopefully that was interesting to you guys. I love this particular question. I wish I could figure out how to word it better, but I do love this question. Okay, so that's it. Anyway, I hope you guys are doing well. I hope you enjoyed the snow. I hope you're having a wonderful Friday, and hopefully this will load fast enough that you guys will get to see it. All right, take it easy. Okay.